Recording in progress.
Let's restart with the second lecture by Surjeet on new experimental searches for dark matter.
Great. Okay, let's share the screen here and go. Okay. So most of today's discussion will be about how one can search for ultra-heavy dark matter. If time permits, I may also make some comments about some thoughts on how to detect inelastic dark matter with some nuclear physics stuff. But I don't know if I'll have time for that, so we'll see. Okay. So in the last lecture, my motivation was the point that if you, how do we make this, that went away, okay, great. So in the last lecture, the main point was that we were pointing out that there's a very large range of possible masses that dark matter could have. Anywhere from about 10 to the minus 22 electron volts if it's a boson, all the way to 10 to the 48 GeV. That's the upper limit from macho searches. And for a fermion, it could be anywhere from about 10 to 100 eV or so, right? So anything above that could literally be the dark matter. And we focused a lot on dark matter that was on the lighter range. Ultralight dark matter from 10 to the minus 22 eV to about 100 eV or so. And then I made some comments about trying to detect dark matter, the direction of dark matter if it's a WIMP, as well as dark matter in the mass from 100 eV to maybe GeV, right? Like in that window, using various new techniques. But today's discussion will be on the other side of the story. What if the dark matter is extremely heavy? Okay, extremely heavy, right? So we're talking about 10 to the 18 GeV or larger, things of that kind. What is the challenge in detecting dark matter that is so heavy? The challenge in detecting dark matter that's so heavy is the fact that it's got a very, very low number density, because obviously its total mass density is fixed. So larger the mass, smaller the number density. Smaller number density, to detect it, you're going to need an extremely large detector. So how do we think about extremely large detectors? What's the main idea that we can make use of? And there's just a point about the world being 6,000 kilometers in size. If you're willing to run an experiment for a year, and you're thinking about, well, if some dark matter went through somewhere in a year, and I want to see it, what is the maximum mass I can think about detecting? That would be about 10 to the 33 GeV, right? So beyond that, it won't even go through the entire Earth in a year. So how do we think about dark matter much heavier than that? So that's the kind of question that we'll be spending time today thinking about. And it'll really be a talk in two parts. The first will be things you can do terrestrially, okay, on various experiments that you can do on the ground. And the next part of the talk, I'll talk about how to use astrophysical objects like white dwarfs, their very existence, as ways to probe extremely heavy dark matter. So this is the first part of the talk, which I'll basically just focus on stuff that goes through the Earth, okay, up to a mass of 10 to the 33 GeV. So I'll give you some very brief thoughts about theory and the phenomenology of these things, and then think about how to detect it while making some comments about current constraints on these kinds of objects. So, the theory of ultra-heavy dark matter. So I call these blobs, okay? There are other names for them, nuggets and whatever. Who cares? It's just a blob, right? That's all it is. And the main point about these things is the fact that we have extremely weak constraints right now on self-interactions in the dark sector, right? We have very good constraints on the dark matter interacting with us, but not very much on exactly what the dark matter is supposed to do to itself. So all of our detection methods so far are fundamentally based on the idea that there is a very large flux of dark matter going through us right now, right? That's why you can, if your idea was that the dark matter was a particle that had a very, very large flux, okay, you can then imagine maybe it has a very weak cross-section with us. So what I'm going to do is build an extremely sensitive detector in which this very large flux regularly goes through, and very rarely I'm going to see a scattering event, right? So every detector that we've built so far is based upon that idea. At the root of that idea is the assumption that the dark matter has weak self-interactions with itself. So it doesn't clump, it doesn't do anything dramatic to itself. But, we have very weak constraints on that. So what if I change that ever so slightly? What if I allow myself to have strong self-interactions in the dark sector? How does that dramatically change this picture? So you may ask a number of interesting questions at that point. If the dark matter had strong self-interactions with itself, is it possible for it to clump up and produce very, very massive objects like that? how does, is there a version of dark nucleosynthesis which would make dark matter particles, fundamental particles, lump together and make complex objects? So by the way, I should have made this point more clear. So when I'm talking about particles of dark matter of 10 to the 33 GeV, I'm not talking about fundamental particles at 10 to the 33 GeV, because we would say if your fundamental particle has a mass above 10 to the 19 GeV or the Planck scale, quantum gravity becomes relevant, it's some different thing, blah, blah, blah. What I'm literally talking about is basically objects like you and me, right? We are 10 to the 27, 10 to the 28 GeV objects, and we are fundamentally made of constituents, protons, things of that sort, which are 1 GeV in mass. It's just we're all like lumped together very efficiently to form these very large objects. Yes?
Don't rotation curves put constraints on how clumpy or how blobby dark matter can be?
Not really. So, there is some constraint from the bullet cluster, which is the fact that we basically know these dark matter lumps went through each other. And so you can sort of talk about, some sort of a constraint from that. I'll make those comments a little bit later, but they're not really that constraining. Yeah, sure. Okay. So there are theoretical questions here, okay? It's like, how can you construct efficient nucleosynthesis? Can you produce it primordially? How do these things evolve in galaxies? Much like what you were just asking, right? These are certainly good questions. And I take the following point of view, which is that the standard model, right, if you think about it, does not actually want to form you and me. The standard model has this very weird fact that the proton is lighter than the neutron. So in fact, it is a case that the standard model does not want to create large nuclei, right? And then if you look at Big Bang nucleosynthesis, there is a very weird fact that deuterium is incredibly weakly bound. There isn't a boron 8 state, right? So if you look at nucleosynthesis, we predominantly only produce hydrogen and helium and nothing heavier than that, because of all these various nuclear physics blockages that actually exist. Now, despite the fact the standard model does not want to form you and me, we exist today, right? And that is because the moment it is the case that you actually have all these interacting theories, the ability for human beings to predict exactly what happens gets extremely complicated. So even though the standard model does not want to form us, we actually exist. So if I had a more normal dark sector, by which I mean, let's say I made up a dark sector in which the dark neutron happened to be lighter than the dark proton. That's just a trivial model I just made up. So if it was that kind of sector, it is not that unreasonable that there could have been an extremely efficient dark nucleosynthesis process in the early universe, where I very quickly take all of my dark matter partons, eat them up, and make gigantic blobs, right? It's not hard to conceive of those things. One can work on these things, and people have worked on them, and I'm going to just assume that given that no physicist that I've come across can explain to me, given the standard model, Lagrangian, right, can you derive the existence of the giraffe? No, right? Lots of complicated stuff actually happens, right? So why should the dark matter not have those things? No reason, right? So let's not worry about the theory, all right? Let's say, suppose this is the case. It's not unreasonable that the dark matter has strong self-interactions. What are the observational effects we can go after? Okay? So the key question is, what can you leverage? Right? Of course, it could be that this dark matter lumps up in such a complicated way and then has no interactions with us, so we can never see it. Certainly possible, but we're going to be hopeful and say, what can I use? What can I extract? What can I leverage to actually get a larger signal and see if I can go and look for it? So the key point we're going to make use of is that when I think about this dark blob, right, it might be that each individual dark matter parton, each individual dark matter nucleus or whatever, has a very small interaction with us. But what's going to happen is that I'm going to take a gigantic number of them and pack them together in one object. And when that object goes through, because there are so many particles now lumped together, perhaps collectively they may give rise to a larger effect than any individual guy. Right? So that's what we can leverage. So what we're going to look for is basically a rare, the rareness I can't do much about because the number density is just small, but potentially spectacular transit, because there's so many particles going through us immediately at one shot. So let's just come up with some sort of a toy model for what this theory looks like so that we can kind of get some idea of the phenomenology, right? So I'm going to think about it as a kind of a nuclear physics model of composite dark matter. There are also other models you could construct, but this is just giving you an idea of what kind of phenomenology might be possible. So I'm going to say the dark matter has some self-interactions, and these self-interactions occur at some scale lambda, okay? Think of it like a nuclear physics scale. There's some dark nuclear physics going on, and the nuclear physics scale is lambda. And I'm also going to assume that the parton mass, okay, the nucleus mass in that sector is also lambda, right? They're roughly the same. You can construct different models by taking hierarchies between them, and that would be a different kind of thing you could construct. And just to get a flavor, let's consider two possibilities. Perhaps these partons are fermionic or these partons are bosonic, okay? And let's see what we get. If they're fermionic, due to Fermi degeneracy, if I pack in a large number of particles together, the object will increase in size, right, because of Fermi degeneracy. And roughly you would say, if I have a blob of mass m, and the scale is lambda, the number of particles is m over lambda, and then the size of this guy would basically scale as m over lambda to the 1/3 or n to the 1/3 times 1 over lambda, right? Thing will puff up. Yes?
Why are we assuming that spin statistics are going to work the same way in the dark sector?
Because spin statistics is extremely hard to violate. I'm assuming the rules of quantum field theory still hold. Yeah. Yeah, so I mean, it's an interesting topic to see what it would take to violate spin statistics, but that would be a very, very exotic dark matter. Yes. The second thing is bosonic dark matter. Okay, what would that look like? So, I mean, I wouldn't claim that all bosonic dark matter models would exactly give you R is order 1 over lambda, right? That's actually not true. All we can say is basically that a bosonic blob can be way more compact than a fermionic blob. Okay, because bosons can be packed on top of each other, and because they're packed on top of each other, it's not unreasonable that there isn't a direct relationship between the actual physical size of the blob and the actual mass that it packs. So I'm going to take this as a limit. Okay, you can in fact construct a variety of models of what are called cue balls, things of that sort, which will interpolate all the way from this limit to this limit. But it's just giving you like limits to some extent as sort of possible objects you could consider. And then I'm going to turn on some interaction between the dark matter, okay, and the standard model. Is what I want to do. So I'm going to say there's a mediator phi, which couples to the dark matter chi in this case, with this kind of a Yukawa interaction, and a triscalar interaction for the case of the boson. I just made that up. I need a mediator between me and the standard model. What kinds of standard model interactions can we consider? And we can consider the usual stuff. I'm going to turn on a mediator mass, mu squared phi squared. That's the mass of the mediator. We'll consider various possibilities, mu being very big and being very small. And then I could have a standard Yukawa interaction between the standard model, between the mediator and the standard model nucleus. I could also think about derivative interactions between the particle phi and standard model nuclei and electrons. I could also think about dilaton style interactions between the mediator and some standard model gauge boson, right? So these are the lowest order operators I can write down. I'm just doing an effective theory analysis. These are the simplest operators I can write down. All right. So what kinds of observational effects can we consider, right? So there are really two classes, depending upon the range of this mediator, whatever mass I actually think the mediator in fact has. And what sets that is basically the de Broglie wavelength of the standard model probe. So what do I mean the standard model probe? I'm going to probe this dark matter blob, right? So you want to think about it a little bit differently than what you're used to. The blob is some massive thing, and I'm trying to scatter individual nuclei with it. Okay, so that's the limit that you're in. And each individual nucleus that you're thinking about has a de Broglie wavelength, right? The mass of the nucleus times the relative velocity between me and the dark matter. And so we're saying if the range of the interaction is small compared to the nuclear, de Broglie wavelength, I would think about that as a short-range interaction. If the range is large compared to that probe, it's going to be a long-range interaction. So if it's a short-range interaction, it's not that different from what you're used to. The dark matter will come and scatter. As it scatters, it's going to deposit energy, and the energy is what you're going to look for in a calorimeter. It's very similar to the standard direct detection experiments that you guys have been exposed to all your life. Okay? What you want to make use of is basically the fact that if it's composite, if there's a large number of particles going through, you might get lots of scattering. It's not just one individual scattering, it's lots of scattering. That's kind of what you want to look for. What about long range? Well, if it's long range, this blob effectively sources a classical field, right? That's what's happening. I have some long-range mediator. I have a blob. The blob is going to create a long-range field. And in the last, talk, we basically talked about how one can use, a variety of detectors to look for the ultralight dark matter things, right? So there are a variety of ultralight dark matter experiments I discussed. They were basically making use of various technologies to detect ultralight dark matter, and ultralight dark matter just a classical field, right? Those are all the effects we look for. And now we are saying, look, those same classical fields may be sourced by these lumps of dark matter. So in the case of ultralight dark matter, we said the classical field itself was a dark matter, right? Those oscillating fields that we talked about. Here we are saying there's actually a lump. This lump is creating a long-range field, and I can now use my detector of ultralight dark matter to detect that long-range field. So it's a little bit different, but not that different. What can we leverage? How can we distinguish this kind of interaction from regular standard model backgrounds, right? That's the main point always. How do you differentiate this from backgrounds? So here's what you really want to leverage. Notice that the velocity of dark matter, which is 220 kilometers per second, is a very interesting velocity. It is significantly higher than the speed of sound in materials. Speed of sound is a kilometer per second, and is also significantly higher than any kind of noise that human beings can create, right? While it is significantly smaller than the relativistic speed of the speed of light. So anytime you've got an experiment that's got really good timing, okay, you should be, and you're making use of the fact that this kind of dark matter, because it's so many particles going through, it's going to typically give rise to multiple events in some detector. If you have really good timing, you can distinguish the effects of this kind of dark matter from any human or material event, which would happen at the speed of sound at the maximum, versus something relativistic, which would happen at the speed of light. Okay, so we can go to make use of this unique fact about dark matter being between these two speeds. So let's briefly discuss the kind of constraints. Yes?
Don't the calculations that lead us to get that value for the velocity of the dark matter assume that the dark matter is homogeneously distributed rather than sort of this clumpy thing?
No, it just requires that the dark matter responds dominantly due to gravity.
Okay, thanks.
That's it, yeah. Because the Earth and the Sun, we also move at 220 kilometers per second with respect to the center of the galaxy, right? So it's just what's called the virial velocity of dark matter. That's it. Now you could ask a different question, which is basically if the dark matter is tremendously dissipative. That is, like there's a force within the dark sector itself that is dramatically altering its properties, then things could be different. But I think that would actually mess up with the overall phenomenology much more. Because we kind of know that overall dark matter does just talk to itself even gravitationally. There is long-range dynamics, it's just gravitational. So what are the kind of constraints that we actually have in this kind of scenario? And how can we think about what's actually happening? But let's get the phenomenology somewhat more clear before we talk about the constraints in that scenario. Okay. So how does the scattering work? Okay. So let's think about the short-range case. And the short-range case is the following thing, right? So all I have is just some big lump of particles. There's a huge number of particles created in one blob. And, I'm going to scatter that against a nucleus, right? So I have a huge number of dark matter particles in one lump, and a nucleus comes and hits it. So of course, what's actually happening is that at the partonic level, right, I have a single dark matter particle, or a parton, that scatters with the nucleus. That's how you're creating the collision. But the partons are not free particles. They're part of that lump, right? So what's really happening is the fact that this guy collides with that guy. And when they collide, some momentum gets exchanged, and that momentum needs to get transferred to the rest of the blob, right? Because I'm not talking about ionizing the blob or things like that, right? So I'm hitting each individual particle, and I'm transferring momentum, and by transferring momentum, I'm moving that entire blob together. So I don't know if you guys are familiar with these kinds of calculations, but there's something called a form factor that arrives in this kind of scenario, okay? And I'll give you the simple, intuitive way of understanding these form factors. So you can ask this question, right? I have this lump, and I want to basically ask, what is the largest momentum I can transfer in this collision without messing up that blob, right? So I know that this dark matter particle is interacting with this particular blob, okay? And I can ask, well, let me, in this collision, transfer a gigantic momentum to this parton. If I transfer a gigantic momentum to this parton, at some level, it will be difficult for this parton to actually transfer that full momentum to the blob, right? Like, can I transfer a momentum that is 10 to the 55 GeV? No, right? Something should go wrong. So what is the largest momentum one can transfer? You can do this calculation, in a very proper calculation, but the answer, okay, is ultimately set to the uncertainty principle, which basically says the following thing. If this parton is not a free particle, this parton is bound to this blob by some forces, And when it is bound to this blob by some forces, it is going to have a Bohr radius, right? Just like how the electron has a Bohr radius in an atom, right? There's going to be some Bohr radius for this particle when it's bound to this object. That Bohr radius roughly sets the uncertainty in the momentum of that particle, right? Because you're not localized it better than that. So it turns out, when you do the calculation in all its glory, this is what happens, that you want to find that if the momentum you're trying to transfer is much bigger than the uncertainty in the momentum of this particle, or in other words, if the momentum you're trying to transfer is much larger than 1 over the inverse Bohr radius of this particle, you're going to get a form factor suppression. Okay, so that's what happens. I'm just asserting that for now, but you will see this pop up, when people talk about atomic dark matter, all kinds of things, right? Is that intuition clear, or does anyone want me to go over that? Okay, but that's intuition, right? That's what it is. Okay, so we're going to say the following thing, that if I'm trying to transfer a momentum that is much larger than 1 over the Bohr radius, I'm going to get a form factor suppression. And I've just made up a model, but I'm taking all of these scales to be the scale lambda itself, right? So anytime I'm trying to transfer momentum much bigger than the confining scale lambda here, I'm going to get some suppression. The kinematics of this process is quite simple, because unlike light dark matter, where the kinematics is set by the dark matter mass, because the dark matter mass is going to be much lighter than the mass of the nucleus, in this case, I'm thinking about dark matter blobs that are so big, 10 to the 13, 33 GeV, 10 to the 18 GeV, whatever. They're way bigger than the mass of any nucleus that we're going to consider. So basically, the kinematics of this process will entirely be determined by the mass of the nucleus, because that's a reduced mass, right? So we have a pretty unique situation here, where we basically say the reduced mass of the system, which is what determines your kinematics in any scattering, is going to be set with the dark matter is going to set the nuclear mass. All right. So we have the fact that the largest momentum I can transfer in this collision is going to be set by the smaller of either the reduced momentum of the system, the reduced mass mn times v. Okay, that's the maximum you can ever get, or the scale lambda. Right. So remember, this scale lambda is a free quantity. I haven't told you what it is. So I can take a variety of values of lambda. So if lambda gets very, very small, I could consider that a very, very soft collision. If that is the case, I can't transfer large momentum to that system, because I have this uncertainty principle preventing me from transferring that momentum. Okay? So here's a very important point about the phenomenology. Lambda is a free parameter for me. So if I take lambda, say less than 300 keV, it's a free parameter. I can take it to be less than 300 keV. What that implies is that I'm transferring a momentum less than 300 keV to the nucleus, right? Because the maximum momentum I can transfer is the minimum of these two quantities. And if lambda by itself is 300 keV, Q could never be bigger than 300 keV. So if you transfer less than 300 keV to a nucleus in momentum, the amount of energy you're giving that nucleus is very small. That means you will not be able to ionize your nucleus. So there are a number of dark matter experiments people look for, where you're very convinced the dark matter will come and scatter and produce ionization. So if I simply take this parameter to be less than 300 keV, no ionization. Ionization goes away. But you'll still be able to deposit heat. So I'm going to just simply consider a range of possibilities, just to consider the phenomenology, right? I'm going to basically take lambda to be a free parameter between 10 keV and 10 MeV, just to give you a range of possible signatures you can go look for, right? And my goal is not to do a thorough, sweep of the entire parameter space to see what's going to happen. I'm simply just interested in asking, is there a reason why experiments should go and look for these kinds of signals, right? That's all I'm really asking. And the key takeaway from this slide is just this fact, that when you're thinking about short-range interactions and scattering, there's a limit to how much momentum you can actually transfer, which is set by the uncertainty principle. And I can just move along that. Yes?
Thanks. So in the small lambda limit, if lambda is also parameterizing our self-interaction scale,
yep,
is it possible that that collision would break apart that dark matter blob?
Not quite, because essentially for you to break it apart, I mean, it can happen. You could try to ionize the thing to some extent, but that is something that you can't really detect that easily, right? But you are right that if I think about lambda being that small, I could also think about ionization in the dark sector. But what can we do with that?
Okay, thanks.
Yeah. All right. So let's think about, that's the overall phenomenology, right? It's true for fermions and bosons. So let's now think about how the phenomenology changes for bosonic blobs versus fermionic blobs. So for a bosonic blob, the main point I made is that it's possible for it to be extremely compact. It could be as compact as the confinement scale 1 over lambda itself. Okay? And I'm taking this huge, this sort of range of parameters, 10 keV to 10 MeV. Lambda is floating between them. And I'm going to realize that basically the largest momentum I can transfer, right, is always set by 1 over the size r, the size of the object, and that is now going to be lambda again. Okay? So the key point about this bosonic blob that is interesting is the fact that now all of these partons are sitting right on top of each other, right? So when I think about scattering, the scattering can get coherently enhanced. So every particle will have exactly the same kind of scattering. Okay? And that means very easily, no matter what the actual interaction scale, of course, if the interaction scale is 0, it won't happen. But very reasonably, it is the case that if there's a large number of particles, all of them scattering at pretty much the same way and it's scattering coherently, right? You can have a huge geometric scattering cross-section in this process. This is a lot like when you have WIMP dark matter scattering, right? You know the fact that, at low momentum transfer, you coherently see the full nucleus. And so you get this A squared enhancement to your scattering cross-section. Here, the A would be the number of particles living in there, which can be a very large number. And thus you can get a very, very large scattering cross-section. So what you can now do is you can go ahead and calculate the rate of energy deposition, which is the dE dx. And dE dx is simply set by the number density of particles in your detector, right? Because you're basically saying this lump is going through you. As a lump is going through you, it's going to scatter a bunch of times. So how much energy do you deposit per unit length? And that is simply the number density of particles in your detector material times the energy deposited per collision. So the momentum transfer is set by lambda. That's the maximum momentum I can transfer. So the energy transfer is lambda squared over mn, right? That's just q squared over mn times the scattering cross section, 1 over lambda squared. So notice that in this particular case, something very interesting happens, that in a large part of parameter space, because it's quite easy for me to get geometric scattering cross section, the scattering cross section is just maximized to 1 over lambda squared. So the lambda squareds cancel off. And I end up getting essentially a universal rate of energy deposition, which is order keV per centimeter. But very importantly, the form in which this energy is deposited depends upon lambda, right? So if lambda is greater than 300 keV, I'll be able to ionize nuclei. So what I'll have this material, the dark matter is going through. As it's going through, it will be depositing energy of order keV per centimeter overall, but it will be ionizing along the process. But if lambda happens to be less than 300 keV, part of my parameter space, I won't get any ionization. I'll just get continuous heat deposition. It's a very different kind of signal than what you're used to looking for. What about a fermionic blob? For a fermionic blob, the main point is that the size has to increase as the number of particles gets larger. Yes?
I just have a quick question about that, the heat deposition. If
Yes.
that's okay. So in a solid material, would that heat deposition just look like a hole in the material?
Not a hole. It would just be, it depends on lambda. So if lambda is
Right.
pretty small, it won't look like a hole. It just looks like phonons.
Okay, phonons.
Yeah,
I see.
yeah,
Thank you.
Yeah. But we will get to holes in a little bit later. So for a fermionic blob, we can think about the fact that the size is going to scale as n to the 1/3 over lambda, right? And it's much harder to get coherent scattering of a fermion, basically because of the fact that as the number of particles in the blob keeps getting larger and larger, the fermionic blob will keep getting bigger and bigger. And if I want to have coherent scattering, I have to transfer extremely soft momentum so that I see the full blob, right? That's the only way I can see coherent enhancement for the full blob, because the blob's getting bigger and bigger. And so you can verify this yourself, that if you want to coherently transfer momentum to the full blob, the amount of energy you're depositing gets extremely small. So for a fermionic blob, the main thing you want to look at is basically the fact that as this blob goes through, there is a large number of particles in it, and therefore it will give rise to multiple scattering, right? It's not just one particle. It's like 10 to the 30 particles going through you immediately, and some number of them will scatter. So there'll be multiple scattering. That's what you want to think about. So you can once again go ahead and calculate dE dx, which is the rate of energy deposition per unit volume, and that is now equal to, again, the number density of the material that you've got times the number of dark matter particles, which is m over lambda, right? When I have a blob of mass m and each parton is lambda in mass, the number of particles is m over lambda. Then there is some scattering cross-section, which should be very familiar to you for, essentially we're talking about a short-range mediator scattering. So there's like a combination of coupling squareds. mediator mass to the fourth times some reduced mass in the numerator. Very familiar kind of stuff. And then you've got this extra factor in here. Okay? This extra factor is a suppression, and that is coming from the fact that if you think about it, right, in normal 2-to-2 scattering, if you have a dark matter particle of, let's say, mass something, capital M, okay, this M, and your nucleus has mass Mn, the phase space is entirely set by the fact that the nucleus wants to scatter, it can scatter in any way possible. Okay, so the nucleus has no constraints on how it can scatter. But notice that in this particular case, what's happening is that I can only efficiently transfer momentum that is order lambda. If I'm trying to transfer momentum larger than lambda to the blob, I'm going to get this form factor suppression, which is what we talked about just in the previous slide. Right? So there's a limit to the largest amount of momentum I can actually transfer in this collision because of the form factor suppression, and that is what this phase space suppression actually is. So if lambda gets very small, you're going to find that I can't actually transfer, I don't have a large cross section because of the fact that I can only essentially do forward scattering where the momentum transfer is very small. So that suppresses your rate here. And then and this of course is the amount of energy that you're transferring, which is lambda squared over mn. Okay. So once again, the form of the energy depends upon lambda. If you have lambda greater than 300 keV, you can ionize. If lambda is below 300 keV, it is going to be heat. What about long-range forces? So I'm going to take in this case, just for simplicity, that the range of the force is very long compared to the size of the blob. So really we're just going to say the blob will source some classical field, right? It has some classical field that just goes as 1 over r times the number of particles in the blob. Right? It's just like if I have a charge, you know, the electric potential is like Q over R, right? So exactly the same kind of thing. What does this do? So if I have this particular long-range force, and this long-range force is acting on nuclei, what's happening? It's basically saying that I've got a lump of object, and this lump is going through some material. As it goes through the material, it'll exert forces on things around me. As it exerts forces on things around me, things will start moving, right? So it will basically transfer heat in that particular process. So that is called dynamical friction. And here's how you calculate it. It's a very simple argument. It says the following thing, right? If you look at this particular formula, notice there is when you have a lump and the lump is going through some material, the lump will exert a force on the material, on some nucleus. So force divided by the mass of the nucleus is the acceleration on the guy. And if you have a lump that is at a distance r from me and it's moving at a velocity v, right, the amount of time it will take, right, is r over v to transit that distance. So all this particular thing is basically the acceleration a times the time t. So this is simply telling me that in a time t, right, the change in the velocity that I'm exerting on this nucleus is the acceleration times the time. So basically we are saying this lump is going through the material, there's a nucleus sitting here, the nucleus is at a distance r from me, the force on the nucleus is f, okay, f of r, the acceleration is therefore f over mn, that's the acceleration, right, and the time it will take for me to transit that distance r is r over v, so this is simply at squared, right, so the energy deposited is mn v squared, and v is basically f over mn times r over v. So this is just kinetic energy. Yes?
I might have missed this, but why are we assuming the field goes like 1 over r?
Oh, because of the fact that I am assuming that you're within the range of the force. If you're outside the range, you don't see anything.
Couldn't it go like 1 over r to some power, though?
It could, but I assume that I'm giving it a Yukawa interaction. So for a Yukawa interaction, it will be e to the minus mu r over r.
Right, sure. Okay, thank you.
You are correct that if I gave it a dipole or higher order interaction, it will be more suppressed. Okay. So I'll ignore this comment. This is really only relevant in the case of bounds from early universe cosmology. So one of the things that I secretly assumed in making this calculation is that I assumed that the speed of transit of the blob is large compared to the speed of sound in the material. Okay. I'm using what is called the instant approximation, where basically we are saying this lump is going through the material, the nucleus is sort of responding freely, right? So of course the nucleus is in a material, and in a material the nucleus is not free. It will, of course, if I pull on it, there will be a force pulling it back, the restoring force. All restoring forces will happen at the speed of sound, of course. And if the speed of transit is fast compared to the speed of sound, I can use the sudden approximation, which is how I made this argument. I'm simply saying it's mn v squared, where v is the velocity that I'm giving, right? That, of course, is false when I'm thinking about this in the early universe. In the early universe, baryons have a sound speed that is basically O to 1. So in the early universe, these effects are much more suppressed, but we'll ignore that because I don't care about early universe cosmology for this particular case. So bottom line, what's going to happen is that if I have this blob and the blob goes through some material, it's going to cause heating. That's all you need to know as an experimentalist. Okay. The second thing it can do is that if this blob goes through your detector and you interact with this kind of interaction, okay, derivative interaction with the spin, that's going to cause a spin precession, right? Basically, this lump is going through you. The lump creates a field. The field is 1 over r. And that 1 over r field interacts with your nucleus through this operator d nu phi n bar gamma mu gamma phi n. That's like this Casper interaction we talked about in the last lecture. So that's a lot like a magnetic field interacting with a spin. So think about it that way. Think about the fact this lump goes through, the lump is creating a dark magnetic field. And what does the dark magnetic field do to spins? The dark magnetic field will cause spins to rotate. The other thing you can do is basically you can couple to electromagnetism, okay, through these kinds of interactions, phi, ff. And what does this do? This is an interesting kind of effect. Basically, this lump is going through. This lump sources the value of the field phi. And I've stuck that in front of the kinetic term of electromagnetism. If you remember your quantum field theory, notice that the kinetic term of electromagnetism sets the value of the fine structure constant. So what's happening is that as this lump goes through, it creates a classical field. This classical field goes out there and basically locally for a small amount of time changes the effective value of the fine structure constant. What happens when you change the value of the fine structure constant? What happens is that if you think about your, well, the length or size of any object, right? The length of an object fundamentally depends upon the fine structure constant, right? Because the atomic bonds, the length of the bond depends upon the fine structure constant. So the fine structure constant changed by some amount, the length of the bond will also change. So what's happening now is that as this lump goes through, the value of the fine structure constant changes, which means the length of an object will change. So I can think about this as a strain. Okay? And the reason why I'm using these words is precisely because we know that we have these ideas on how to detect ultralight dark matter with, say, experiments that look for spin precession and experiments that look for acceleration, which are like gravitational wave detectors, which essentially measure strain. Right? So you kind of map in your head that as this lump is going through, it's depositing heat. That's very normal. It's what you've always been used to. But it can also do these additional things, such as cause spins to precess, as well as cause strain on objects. So let's think about constraints. All right? So there are a variety of bounds you can place. It is basically that there are these bullet cluster limits. So that's really all we know about self-interaction of dark matter, is that we know the dark matter went through the bullet cluster without hitting itself. Okay? So there's a limit on that. That limit is basically like something like a centimeter square per gram. Okay? Or rather, it basically says that if your dark matter parton has a mass of a GeV, the self-interaction cross-section is somewhat smaller than the strong interactions. So it's not a very significant bound at all. So for short-range interactions, and if it's a boson, there really isn't any actual bound. Because basically, if you think about it, bosonic blobs can be extremely compact. And I can pack a huge number of them in a single boson, which means that the relevant quantity, which is the cross-section over the mass, can be extremely small, right? Because the cross-section is simply set by the bosonic size, which is the scale lambda, and I can put a huge number of particles in that. So for bosonic blobs, we have literally no real constraints from bullet cluster. For fermions, you can, depending upon the parameter space you take, you can certainly have constraints because fermionic blobs get fairly fat, okay? But notice that all of these bounds on the bullet cluster really only exist for dark matter that's the full dark matter. So if you had a constituent of dark matter, that's say 10% of dark matter, which was in these very fat blobs, there really aren't any limits from the bullet cluster. And this is not that unusual. If you look at the standard model, right, you and I are big lumps. We are less than 1% of how the standard model chooses to distribute its particles, right? So 99% of the matter, the baryonic matter, is existing as individual particles, right, as protons in the galaxy. Only a very small fraction of them clump and form very complicated objects like you and me. So if I have a complex dark sector, it is not that unreasonable that a 90% of the dark matter exists as individual partons, but a small, say 10% of it, lumps together and makes complex objects. So I'm interested in the full phenomenology, so I'm not going to take this bound all that seriously, because I'm going to say, yeah, maybe I lose a factor of 10 in my overall number density, so what? Right? The blob is still interesting. It's just the fact that we know so little about it. Yes?
Thanks. Could you repeat just qualitatively where the bullet cluster bounds come from that we do have?
It's coming from the fact that as the bullet cluster, so what is a bullet cluster observation, right? It's basically saying that, look, the bullet cluster, these things went through each other, and I saw the dark matter here and the dark matter here. So imagine the dark matter scattered with itself. It wouldn't have gone through, right? So that basically says that the fact that the dark matter went through is a statement that if I take the mean free path of dark matter, which to scatter with itself, the mean free path better be longer than how long it took for the thing to go through. And so if you convert that into a bound, you will find, so what can you bound? You can basically only bound cross-section over the mass of the dark matter because of the fact that you need to know the number density of the dark matter, right? So basically, if I only had one dark matter particle, it's extremely hard for it to hit itself even if it has a large cross-section. So that's where the bound comes from, sigma over m. Yeah, good. The other kind of bound is basically the fact that if these blobs exist in the early universe, you may worry about things like baryon acoustic oscillations because this blob is scattering with all kinds of standard model particles, and that'll cause some kind of friction. Okay? So we know that baryon acoustic oscillations work. The dark matter. So what would happen is basically the fact that if you had, let's say, interactions between the dark matter and the baryons during BAO, as the dark matter structure tries to grow, the scattering with the baryons would damp it. Right? Like we have very good evidence in the CMB that the dark matter structure grew very nicely due to gravity. We don't see any extra interactions there. So that is A bound. Turns out this is not a significant constraint at all. Right? You can put in the numbers. I'm not giving you the answer because it's kind of a theory thing. But you can work the numbers. It's not a significant constraint. I will impose one reasonable constraint on this, which is basically I've turned on a new force in the dark sector. Right? I'm basically putting a new blob. This blob I'm saying has a large number of particles, and as it has a large number of particles, I'm also turning on this new interaction between itself. And of course, we know in the standard model, for example, if I take a large number of particles and I turn on a gigantic Coulomb interaction, at some point the thing becomes unstable because the self-interaction energy becomes so big that the object will rip itself apart. So there's a bound from that, and essentially you can work this out, that it basically says if you want to have a blob with n particles in it, okay, the self-interaction strength, the G chi, better be smaller than 1 over square root of n for the case of bosons and 1 over n to the 1/3 for fermions. I'm not going to go through it. This is simply, this assumes the fact that the self-interaction strength is also the same scale lambda. That's all, right? So that's basically how it works. All we're basically saying is the fact that if you have this new interaction with the particle phi, it better be the case that the total energy doesn't become larger than lambda itself. It's a stability bound. So let's talk about constraints. What have people done that has probed this kind of scenario? So there's actually a very interesting experiment done by Marty Pearl. It's called Macro. I think it was actually done in Gran Sasso. So what he did was he got himself an 80 by 10 meter by 10 meter cube amount of scintillator, okay, some gigantic amount of scintillator, and put it in Gran Sasso. And he was actually looking for magnetic monopoles, okay? And but he accidentally also happens to set limits on dark matter this way. And the idea is the following, that basically he had this very section detector where he's got like number of scintillator modules, okay? And he's basically looking for a magnetic monopole going through this material. As it goes through this material, it will deposit energy in all of these scintillators, okay? So as it transits each of these scintillator layers, it's giving out light, and he's basically saying, do I see something going through at the speed of 220 kilometers per second? Because that's what something virial is supposed to do, as opposed to radioactive background or something else which will move at a different speed. Okay? So what he managed to do was really get a large volume, right? 80 meters, like a football field, basically. That's huge. And but his experiment required two things. His experiment required that whatever went through create scintillation light. Okay, that's how you were able to see something is going on. And that set a threshold of 6, and also he required 6 MeV per centimeter of energy deposition, okay, for him to call that an interesting event. Otherwise, it was just background for him. So Marty Pearl's experiment basically says something goes through, it deposits 6 MeV per centimeter, and it better be the case that whatever is doing that causes scintillation as well. It causes ionization. Otherwise, you would not be able to see it. Okay, so that's a laboratory constraint. It's also the case that when I'm turning on this particle phi that interacts with the standard model, that particular coupling, phi times the standard model coupling, is constrained by all the usual things. It's constrained by searches on new forces because I've turned on a new Yukawa interaction between the standard model and a new particle phi. We search for those. There are also astrophysical bounds on these guys, right? All the usual stuff. They all exist. So let's just talk about the signals, right? What would you look for? I realize a bunch of this was fairly dry just in terms of telling you what the phenomenology looks like, but okay, you ought to start somewhere. But here's what you go look for in the case of an experiment, right? Here's what you look for, right? So you basically say, what if this scale lambda, which I don't know what it is, it was bigger than 300 keV, what can this thing do? What this thing will do is basically for short range interactions, this blob is going to go through your detector. As it goes through your detector, it will scatter multiple times. So you're going to look for multiple scatterings in your detector happening at a time set by the 220 kilometers per second. So you want really good timing resolution, and you say, this event happened, this event happened, this event happened, and it is a case that the time between the events is consistent with the transit speed of 220 kilometers per second. Okay, so you want good timing, you can do that. What constrains this parameter space is that whatever d dx you're looking for better be smaller than 6 MeV per centimeter. So when I show you what you can look for, I will impose that constraint because otherwise you're ruled out by macro. Another idea that's actually possible is that actually one way to get an enormous volume in these kind of experiments is that you can basically imagine the following kind of setup. Okay, the dark matter can say transit through ice. As it transits through ice, it can heat up the ice locally. As it heats up the ice locally, the ice will melt, not really melt, it'll do some expansion or something. It'll cause a sound wave. Okay? So you can go to something like ice cube and stick these ice phones or hydrophones or whatever in the ice and hear sound. Okay? And you want to basically put a network of these guys, and you want to see if you're seeing sound waves that strike multiple detectors at a speed of 220 kilometers per second. So that's going to be distinct from shrimp and ice and other kinds of, whales, things that normally make sound in ice or water or whatever, right? Because the speed, once again, very importantly, is much faster than any sound speed that humans or animals can make. Okay? So that just requires some DEDX of a keV per angstrom, but you can construct models where that also happens. The other possibility is lambda is less than 300 keV. When lambda is less than 300 keV, I don't really create any kind of ionization at all, right? So the standard searches, for example, like what macro was doing, don't apply because there's no scintillation light anymore. So there isn't really a constraint on these kinds of things. But you can actually use low threshold calorimeters like CDMS, Edelweiss, Crest, these kinds of people, right? Where if you're actually interested solely in energy deposition and not so much in ionization, what you look for is a line of hot cells in CDMS. You'd be like, I saw some phonons here, some phonons here, some phonons here, a line of hot cells. Once again, you combine that with really good timing. So you want to say this block of CDMS lit up, this one lit up, this one lit up, and the transit time is that of dark matter and not due to some kind of vibration, stuff like that. Right? So timing is the key. Yes.
I think I'm missing something very, very basic. So in the first two, so in the macro and the acoustic, do we need multiple scatterings in the detector?
You typically will have it because I'm talking about very large energy deposition.
Okay, so it's like a cascade effect that gives you the signal.
Yeah, it's like multiple things happening. Yeah, like I'm always choosing parts of parameter space. So it turns out that for detectability, right, I need enough of an energy threshold because these are like large volume detectors. So I'm already forcing myself to deposit enough energy per collision that I'm getting multiple things like this.
Okay, but it's not multiple collisions in the detector, right? It's just one collision and then...
No, like essentially you're hitting one guy, right? So I should have said this earlier. So notice that there's a limit, right? Where basically when I'm colliding, the maximum amount of energy I can give in any one collision is limited by the mass of the nucleus. So I can never give more than a few keV per collision because the nuclear mass just fixes what that can ever be. So when I say a keV per angstrom, I'm basically saying I'm hitting every nucleus as I'm going through. So there will be multiple events.
Okay, thanks.
Sure. What about long-range mediators? So here we can think about different sets of ranges, but I have this very rare transit of very heavy dark matter, so some lump that is going through the Earth. Think about it as a dark asteroid, something like this. What it's doing is that it's going to create this classical field around it, right? It's just sourcing this 1/r field around it. And as it goes through the Earth, this classical field, if it has a long enough range, it can excite multiple detectors around the planet, right? So for example, as this thing is going through, let's say the range of this field happens to be 6,000 kilometers, and let's say you have two experiments that are looking for spin precession, say 2 Caspers or something like that. What's going to happen is that as this guy goes through, right, there is this dark magnetic field, something like this, that will excite a spin precession experiment here and a spin precession experiment there. Okay? Now nominally, every experiment, if it just looked at itself, it will basically say, that's just some noise. I'm going to throw it out. But now if you do a time correlation, a cross correlation, you'll be like, my God, I saw something, a strange anomalous spin precession in one experiment. At the same time, I also saw an anomalous spin precession experiment in a different experiment 1,000 kilometers away. And that keeps happening all the time. When that is the case, by doing cross correlations, you can convince yourself that what's actually happening is a cosmic event, okay, a dark matter event. And it's also the case that this guy, let's say the range is 6,000 kilometers, when it transits through the Earth, the time it takes will be 6,000 kilometers divided by 220 kilometers per second. So the signal will last exactly that time, right? So once again, by doing this cross correlation and making use of that time, you can figure out what's happening is actually a dark event. And this is not just true, by the way, for experiments that look for spin precession. It's also true for these gravitational wave detectors. So we talked about how these particles can also source long-range fields that effectively cause accelerations, that also can cause strain because they change the fine structure constant. So you could have LIGO and Virgo, for example, and you would see signals. It'll be a very sharp transit, right? Basically, this thing is going through. There'll be a sudden strain in LIGO and a sudden strain in Virgo. And if you did not know that if you didn't do a cross correlation, in each experiment you would just think it's just some background noise. But when you do the cross correlation, you can then figure out what's actually happening is something due to dark matter, right? So in my opinion, there's a good reason to actually look for these kinds of correlations between detectors at this interesting time. So normally in LIGO and Virgo, you're convinced what you're looking for is a gravitational wave. So you're looking for something that happens at a speed equal to the speed of light. But I think another speed you should be looking for is 220 kilometers per second because that is tied to dark matter. So, I mean, there's a bunch of parameter space you can look for. Like that's just for you to go get money for the experiment. All you want to say is that, yeah, look, there's some stuff you can cover. Okay, that's basically it. So there's a bunch of things you can do. Let me move on to something that's a more recent interest of mine, which is paleo detection, right? So for long-range interactions, if you looked at the slides that I showed so quickly, you would realize that I could actually probe dark matter all the way through 10 to the 33 GeV, where we're basically saying one lump goes through the Earth once a year, right? And I can still see it because there's a long-range force that is 6,000 kilometers. So good, there's some part of parameter space I can probe. But for that, I had to assume that there was a 6,000 kilometer range force, right? That wasn't given to me. I just made that up. What about short-range interactions? The dark matter could very reasonably be short-range interactions. So if that's the case, I cannot possibly have, is that a question? Okay. I cannot possibly have a, a kind of thing that I talked about where I can't excite multiple detectors simultaneously because the range of the interaction is so short. So we cannot build planetary scale detectors for short-range interactions, obviously, right? Nobody will give you the money to do that. What can you do? What one can do is leverage time. The Earth is very old. So notice the following piece of mathematics. If I have a 1 meter squared area and I'm able to observe events in that 1 meter squared area for 1 billion years, that's effectively the space-time volume of 10 to the 9 meters squared year, which is effectively the same thing as building a 100 kilometer squared area operating for a year, right? That's a simple mathematics. So effectively, if we are able to use time in some way, one should be able to probe very, very large dark matter masses, very, very rare events, because they would have very rarely gone through the Earth in the lifetime of the Earth. So that is the idea of paleo detection. And the key point here is the following. I want to mess up rocks, right? That's my idea, fundamentally. To mess up rocks, chemistry and geology, they operate at the EV scale. As far as dark matter is concerned, the EV scale is irrelevant, right? The EV scale is all about chemistry. The dark matter can deposit whatever energy it wants. It depends upon the physics of the dark matter. So there can certainly be dark matter that is so soft it won't do anything. Fine. But it's not that difficult for me to construct models of dark matter, or at least go search for dark matter models where the energy deposition is much above the EV scale. And once I'm easily able to deposit energy above the EV scale, I can very easily mess up chemistry and geology. All right? So that's the basic idea, right? So I'm not the first person to propose this, by the way. So the idea basically is that I take some rock, there is something goes through the rock. As it goes through the rock, it deposits more than a few EV as it goes through. And once it does that, it's going to create all kinds of defects in the rock, which you can go look for, right? So the main point here is the fact that dark matter can very easily create distinct tracks, right? All kinds of things can cause cracks in your rock. So you need something that's very distinct from the dark matter, something that you can't see otherwise. You also require clean and old geological samples that you know have been around for a long time and don't have a whole lot of geology going on in there. And the fundamental ability for you to look at these tracks is limited by how easy it is for you to scan some rock and find out that there's something crappy going on in it. Obviously, the larger the volume of rock you can sample, the more easily you can find these things. So this, by the way, was demonstrated by Buffett Price back in the 80s, my former colleague at Berkeley. So what he did, okay, it was a beautiful experiment, is that he found some mica, okay? Don't ask me what mica is, okay? I'm a theoretical physicist. I have no idea what mica is, okay? Some material. And what he did was he took this mica and he wanted to find tracks in the mica. So the main thing is that your tracks are going to be very small, right? So how do you see the small tracks? So what you basically do is that you take a sheet of mica and then you pour some acid on it. And when you pour some acid on it, like little bits of it, I guess, the acid will slowly go through the holes in the mica and make them larger and larger. And once they become large enough, you can just use an optical microscope to just literally scan with his eye and find out where the holes are. So that's what he did. He took mica, put some acid on it, wait for a couple of days, the holes get big, and then he took an optical microscope and then went around and tried to find tracks. Okay? So that's demonstrated. He actually, back in the day, used this to put limits on WIMPs and stuff like that, even look for proton decay back in the day. Okay? And he was primarily interested in probing magnetic monopoles. That's what their big thing was. But the key limitation of Buffett Price's idea was that, he had to, since he was using an optical microscope to look at this, yes?
Sorry to interrupt. In these experiments, would the tracks from these composite dark matter particles look different than like small meteors or asteroids?
You just go a little bit deeper underground, right? So meteors don't really penetrate underground.
Okay.
Right,
because they're coming in with less energy, I guess, than the dark matter?
No, I mean, rocks just hit rocks, right? So they're not going to go, like if I go, 100 meters inside,
right,
meteors don't get that deep.
Okay.
Right. So the real background that Buffett Price actually has is things like radioactivity. So you look at like stray radioactivity because everything contains a little bit of uranium. And so what is important for that experiment is the fact that if you look at radioactivity, right, like you produce an alpha. The alpha will probably go a micron and stop. So what's important in all of these cases is that the dark matter or the magnetic monopole, it just goes right through. So it's going to create a very, very long track. And that's what you're going to make use of to distinguish it from things like radioactivity. Yes?
So I guess a method like this would probably be much more sensitive to something like these bosonic blobs, right? I mean,
sure.
If you had something like a fermionic blob, I mean, I don't know, wouldn't that be a very...
well, it all depends upon the parameter space and what you can construct. So I'll show you models you can build where even for fermionic blobs you can make it happen.
Okay.
Right, it's just that it's a very open parameter space, right? So, but you are correct that in general bosonic blobs, should do better. So the key limitation for Buffett's idea was the fact that he had to, with optical microscopy, you have to make the holes bigger to see it with his eyes, right? And so he had to put the acid. And so he has to start with a very, very clean geological sample, and there's only so much clean mica that he could get. So we're going to use newer classes of techniques to actually look at the stuff. So the idea basically is the following, that what we're going to look for is basically these kinds of dark matter blobs as opposed to magnetic monopoles. A magnetic monopole is a very specific thing. You've already put your mind on what it is. So the dark matter, pretty open part of parameter space. What I'm going to assume is the dark matter goes through, as it goes through, it deposits enough energy as it transits to melt micron-sized cylinders of the rock, essentially. So the dark matter just plows through, very heavy. As it goes through, I'm going to find parameter space where it basically melts the rock. Okay, and that's something that doesn't really happen in geology that easily. And instead of acid etching, okay, which is a very difficult process we talked about, which makes holes bigger, we're going to use more modern techniques, which are essentially electron microscopy, where it's a lot, I mean, it's like X-ray microscopy, right? I can use X-rays to find cracks in your bones, fractures. Similarly, one can use more modern readouts like X-rays or electron microscopy, which will find cracks in this material. And the key point is that I'm not pouring acid, so I'm not going to amplify any defect that already exists in the material, right? I'm just getting it, I'm just shooting something through and seeing what's in there. So that basically allows me to use a wider class of geological formations than what Buffett Price was able to use. So in particular, we talked to these geologists. So these quartz veins in the Jack Hills of Australia, it's supposed to be one of the oldest parts of the world, and the billion years old or whatever, and it's pretty easy to get tens of meters squared of the material. So that's the plan. We're going to try to get some of that material and scan and see if we find holes in it. Okay? So once again, there's a bunch of parameter space that you can go probe. Basically, I'm asking, what does it take for me to actually create a micron size hole in these rocks? Yes, sir.
So once you pull these samples out of the ground, how are you able to discriminate tracks left from dark matter or monopoles and from cosmic rays or even muons?
Very good. So cosmic rays and muons, they're not going to actually cause continuous tracks like so I'm talking about a lot of energy deposition, right? So if you think about a muon, the muon, it's something like a few eV per angstrom. It doesn't really do anything that damaging. It won't create these long, continuous micron-sized holes in it.
Thank you.
Sure. Yes.
I can talk about, or wait. Okay, I'll talk about.
Yeah.
So I guess I'm wondering, these events are so rare. Let's say you scan this massive
Yep.
rocks.
Yep.
You see one track.
Yep.
Can you make a scientific conclusion based on one track?
Yeah, because it'll just plow right through, right?
But couldn't that be something else? Like, how can we really say that?
You can, because essentially you'd be like, in a sense, if you found such a thing, right? You could in principle, like, because you're doing X-ray readout, something like that, you can literally track it for quite a distance, okay? And not only that, you will find, so the ideal thing would be the following. You basically get a very nice set of rock, which is what this quartz is. You just get like a tiny micron hole drilled right through with nothing going on around it. The geologists don't know of any such phenomenon that would give you a nice cylindrical micron hole with nothing around it. And it's like melted too, right? So it's like essentially very localized melting. Nothing in the standard model can give you that.
Cool. Thanks.
Yes.
So if this blob is of a mass of 10 to the 33 GeV, I guess it's quite macroscopic, right? Why
Yeah.
should it do just one micron-sized long track?
Because the thing is, remember, the parameter space here is not set by our scales, right? It's set by whatever the scale of the thing is. So I've picked parameters, for example. So there are certain parts of parameters where the holes would be bigger. There are certain parts of parameters where the holes would be smaller. So if we just prove, for me here, the point is more like I'm going to go look for this. Is there a part of parameter space where things make sense? I'm just demonstrating that it does. So the scales here are not set by our mass scales, right? So if you and I, our size is set by the keV scale of atoms. If the strong coupling scale that set our atomic scale, let's say was, I think in this case it was 1 MeV, a 10 to the 33 GeV object would be extremely small. Okay? Because remember, the density goes as, lambda cubed, right? Yeah. So let me move on to the last part of my talk, which is I'm thinking about even heavier dark matter, extremely heavy dark matter. 10 to the 19 grams, things of that kind. And I'm going to think about how I can use that to blow up stars, okay, and use that to think about dark matter. I'll tell you the story here. So here's a basic idea, okay. I have a white dwarf. And I would like a single dark matter event, okay. And just the example of what we'll talk about is essentially a transit of a primordial black hole. That's what I'm going to talk about. But this can also be extended to many, many models. So here's the idea, okay? Think about a primordial black hole, right? So I have a white dwarf there's a primordial black hole. The primordial black hole goes through the white dwarf. It doesn't stop or anything, right? It's a big heavy thing. It's just going to plow through it. As it plows through it, it's going to heat up a cylinder in that white dwarf, leads to localized energy deposition. And I'm going to claim that it's possible that these things actually trigger that white dwarf to explode as a type 1a supernova. And so the idea would basically be that given that we have seen sub-Chandrasekhar mass white dwarfs, we've seen them all the time, there are some limits on this kind of stuff. And that's the idea. And I'll talk about how my thoughts have evolved in that process also. But initially, I used to think this was just a question of setting limits. But I think there are some interesting games to play now. So first of all, just as a detector, if I want to think about this kind of detector as a dark matter detector, what is it, right? I've got a single dark matter event that's going to cause a type 1a supernova, all right? How good of a detector is it in terms of detector capabilities? Well, a white dwarf is something like several thousand kilometers in size, okay? Not only that, as something falls in, I get a gravitational enhancement of the number of particles it can swallow up, right? So this is sort of a gravitational focusing, if you will, right? So the white dwarf has some escape velocity that's something like 10 to the minus 2. So it's in fact the case that when something is going around the white dwarf, even though it doesn't actually cross 4,000 kilometers, even if it's somewhat far away, the white dwarf can swallow it up due to its gravitational force. And that's a gravitational focusing boost of about 1,000 on that. Plus, these guys are around for several billion years, so it's like a lifetime of something like that. And when this thing blows up, you can see it anywhere in the universe. So it's a pretty nice dark matter detector if you can make it work. So this is a large space-time volume detector, and it's ideal for ultra-heavy dark matter that of the kind I'm interested in, such as primordial black holes, cue balls, things of that kind. So let me give you the outline, right? So I'm going to tell you, why is this possible? Why is there a possibility of runaway fusion in white dwarfs? I will simply demonstrate the idea for primordial black holes, but as I said, there's a number of other things you could constrain or see that way, and then we'll talk about observational constraints and conclude with future directions. All right, let's try to blow up a star. What is a white dwarf? Okay, 101, this is all we need to know. A white dwarf is basically a stellar remnant. It's supported by electron degeneracy pressure, right? It's a dead star. And the famous Chandrasekhar limit is that if the star is more massive than 1.4 solar masses, it will collapse. And if you look at typical densities for white dwarfs at 0.5 solar masses, its density is around 10 to the 6 grams per centimeter cube. It's a very strong function of the mass. So when the mass goes from 0.5 solar masses to 1.3, the density spikes up by a factor of 1,000, right? It's because it's about to blow up. And there are a couple of kinds of white dwarfs. Some of them is basically depending upon their evolutionary history. Some of them are dominantly carbon and oxygen. Some others are oxygen, neon, and magnesium. And it depends upon stellar evolution, how they actually form. Single white dwarfs are typically carbon oxygen. If they're formed in some other thing, there'll be something like that. Here is the main point about white dwarfs, okay? The core of a white dwarf contains carbon and oxygen, and those guys want to fuse, right? What happens in a white dwarf is basically as the star gets closer and closer to 1.4 solar masses, carbon and oxygen will start fusing with each other, oxygen and neon will start fusing with each other, and they fuse. When they fuse, they produce energy. That energy will cause other guys to fuse as well, and they cause even more fusion, and the whole thing explodes as a nuclear bomb. So that's what it is. A type 1a supernova is a nuclear bomb, okay? And our bounds, or the discovery of dark matter, if you want to place, is going to be coming from how dark matter can cause supernova to explode well below the Chandrasekhar limit. How is that possible? So let's see the main idea, okay? The key point is that nuclear fusion rates are exponentially sensitive to temperature. So when I have carbon and oxygen, they want to fuse. They want to form whatever they fuse and form, but usually they don't because of Coulomb barriers, right? Electromagnetic repulsion keeps them away from each other. So at low temperature, they don't want to fuse, even though they would ideally want to. So if you look at the fusion rates at a temperature of 300 keV versus 10 keV, so this is a factor of 30 in temperature. The fusion rate goes up by 10 to the 30, right? Because at 10 keV, you've got a Coulomb barrier, so you've got an enormous exponential suppression of fusion. While if you go to 300 keV, you've got enough kinetic energy, you penetrate the barrier and you fuse. So a factor of 10 in temperature can increase the rate by 10 to the 30. Now somehow if you manage to cause some fusion to happen, every fusion will release tens of MeV of energy, much higher than the 300 keV they start off with, which means the moment you start some fusion going, the energy released in every fusion is much bigger than the energy temperature you needed, so you're going to create more and more fusion, and that's how you blow up. Right? So a chain reaction is possible in the system, and it's possible, therefore, that a small number of initial fusion can trigger many more reactions, because I only need, let's say, 300 keV, and every one of these fusions is giving me 10 MeV. Right? So a small number of initial fusions can go on and create more and more of these guys. So let's ask, what does it take for this runaway fusion to happen? The first thing I need, of course, is a local increase in temperature. Right? So the first thing I tried to do when I realized this was to try to blow up the sun. Okay? Can dark matter blow up the sun? Turns out you can't blow up the sun. It's a good thing. Okay? So why can't you blow up the sun? You can't blow up the sun because the sun is basically an ideal gas. And what that means is that the pressure of the sun is always sensitive to its proportional to its temperature. So let's ask the following question. I take the sun, and I'm going to take up a small part of the sun and heat it up, right? Because my hope was indeed that. I heat up a small part of the white dwarf, it's going to blow up. So what happens if you take a small part of the sun and heat it up? Can you do something with it? What happens is that because the sun is an ideal gas, as you heat up the sun will expand. The pressure increases, the sun expands, and as it expands, it just cools. It's a stable system. It's a good thing, otherwise the sun may not have existed. A white dwarf, on the other hand, wants to blow up because a white dwarf is a degenerate gas. The density and pressure of the white dwarf are independent of temperature. Right? So if you take the white dwarf and you heat it up, the density and temperature don't care. The density and pressure don't care. Right? So there is no automatic self-regulation. It doesn't automatically expand and cool down. Right? So when you heat up a small part of the white dwarf, the temperature just increases. It doesn't cool down. And that means there is no self-regulation. It's fundamentally an explosive object. So let's ask the following question. I take a white dwarf. I heat up a region of size delta in the white dwarf to a temperature T. And I'm going to say the temperature T is much bigger than the ambient temperature of the white dwarf. Say this is 10 keV, this is 300 keV, something like that. What can happen? Right? Two things. We talked about this last time in the case of the magnetic bubble chamber as well. Two things can happen. Heat from that region can dissipate out through scattering. That will lower the temperature. Or fusion can happen. And fusion happens, you increase the temperature. So two possibilities. If the dissipation rate is faster than the fusion rate, whatever energy you put in there will fizzle out. There's no explosion. If the fusion rate is faster than the dissipation rate, it'll explode. That's it. So the very straight standard calculation, you do the heat equation, you basically say, look, given its initial temperature, and the size delta that I heat up, how long does it take for the heat to diffuse out? Okay. This is this random walk that we talked about, right? The heat so if you take a white dwarf and you heat up a region size delta, basically the larger the value of delta, the more time it takes for the heat to diffuse out because it's a random walk. It goes as delta squared. And it depends upon things like conductivity, specific heat, and all that kind of stuff. Okay? So what you fundamentally realize is that if you take this white dwarf and you heat up a sufficiently large amount of it to the temperature that you want, the diffusion rate will be automatically slow because you have to go a longer distance to get out, while the fusion rate is independent of delta. Right? The fusion rate just depends upon removing some Coulomb barrier. Right? So as long as you heat up enough of a white dwarf to this temperature, the white dwarf will explode. It has no option. Right? And basically, once you start fusion going somewhere, you can't put it out. Right? Every fusion releases 10 MeV. You heat up even more, it just explodes. That's what happens. So you can go and calculate how large of a white dwarf you need to heat up. Okay, I'll just quickly make the main points, which is that this is a complicated calculation. It depends upon what the heat carriers are, photons, electrons, all this kind of stuff. And there are various formulae for these things, which I won't really go through. Other than pointing out that these things depend a lot about density and temperature and stuff like this. And the main point about all of this is basically that I didn't do those calculations. Serious people did it. Okay, so they know what's going on. All right. And this, rate of fusion also is exponentially sensitive to temperature. Okay, so I'll actually not talk much about this. I'll just talk about the serious people. Okay, not me. All right. So these things have been calculated by people who care about why white dwarfs explode. Right? People who want to understand type 1a supernova. So the standard paper on this is basically Timms and Woosley from the 90s, and they did this very simple calculation. They basically said, what is the minimum size delta that I need to heat up in a white dwarf to, say, a temperature of an MeV for me to cause an explosion, right? They did this calculation for various densities of white dwarfs. So I just used that answer basically, all right? And what they found is that if you take a white dwarf that has a density of around 10 to the 8 grams per centimeter cube, all you have to do is to heat up a region of size 10 to the minus 4 centimeters. Think about how small that is, to a temperature of 1 MeV. So if you heat up a region of size 10 to the minus 4 centimeter cube or cylinder or whatever to 1 MeV, you will cause the white dwarf to explode. Okay, very easy. And if you convert that to particle physics units, that's an energy of around 10 to the 18 GeV, that's it. So somehow you're able to deposit 10 to the 18 GeV within 10 to the minus 4 centimeters, you will cause the thing to explode. Okay, this thing is sort of density dependent, it turns out. So, at lower density, it scales somewhat differently, but rather rapidly with the thing. But these are details, right? We don't have to worry about this. So what we did was we actually looked at the actual equations of state of white dwarfs and stuff like that to extract, various densities. Yes.
So thinking about these bounds, are there error bars on the Chandrasekhar limit, or is that set?
That's set by fundamental physics. You just need to know the mass of the electron, the gravitational constant, that's it. Okay. So what you can do is you can look at various equations of state and compute various trigger masses. That's basically what it is. So you basically say if you're a 0.7 solar mass white dwarf, because of these complicated density dependencies, you have to deposit MeV temperature. I mean, you have to basically set 10 to the you're going to take all the particles within 10 to the minus 2 centimeters and make them 1 MeV temperature to make that guy explode. While a 1.3 solar mass guy, all you need to do is take 10 to the minus 5 centimeters and make all the particles in their MeV temperature, the thing will explode, right? So you can kind of see how sensitive it is because, of course, it makes sense. The closer it gets to 1.4 solar masses, the thing just wants to blow, right? So you get very, very rapid dependence on these guys in terms of the mass of the white dwarf. That's the main takeaway point from this slide. So let's just quickly talk about primordial black holes, right? So you probably had some lectures on primordial. There's a question, yes.
Yes, so these constraints could come essentially from looking at the explosion of supernova, but how do we know the mass the white dwarf had before the explosion?
Very good. So you actually look at the brightness of the white dwarf, and you basically see, I mean, I'll actually comment later on, because I used to think that type 1 supernova were well understood. Turns out they're not. So basically, you look at the amount of nickel 65 or whatever is coming out of this, and you use that as a way to infer the intrinsic mass of the explosion itself. Because once you get this guy going, the amount of nickel that you're going to get at the end of the day is basically set by some nuclear code, right? So you kind of look at the brightness in some sense and use that to figure out what the original mass used to be.
I see. Yeah. Thank you.
And some set of constraints just come from the fact that, look, I've seen this white dwarf. It shouldn't exist if all this dark matter stuff was going on.
Hi. So this all these white dwarfs are being triggered by primordial black holes, but can other things trigger it? Like some random stuff just heats up a portion of your white dwarf and then trigger it to explode.
Well, I mean, are you asking random standard model stuff or other things?
Other things can be can just a normal black hole that happens to be passing by and then just
a normal black hole would be 1 solar mass, right? So that thing will just eat up the primordial this white dwarf. So it's a weird thing. The standard model gives you 1 solar mass black holes, and if your white dwarf goes next to a 1 solar mass black hole, the black hole just eats it.
Right.
Right. So this is an interesting scenario where the black hole is so small. 10 to the 19 grams is incredibly small. So it'll just go through. It doesn't do much to the white dwarf other than blow it up.
Oh, okay. So the ingredients is to have this small light black hole that's somehow stable and passes through a white dwarf, and then you trigger it.
Yep.
Okay.
Yep.
Cool. Thanks.
Yes.
No, I have a related question with the boys. How do you prevent the white dwarf to self-explode? Because this seems like a little threshold to explosion. It's a little amount of energy. So
say that more slowly. So how do I prevent the white dwarf from exploding? Or
no, because I mean, for this, I don't know if I understand this right, but with this little amount of energy, I think anything could make them explode,
so you're asking
rays, gamma rays or something.
Well, look, it's not that little. It's 10 to the 18 GeV, right? And secondly, this has got to go. It has to penetrate a little bit in the core.
Okay.
Right? Because what happens is the fact that the surface of the white dwarf is probably like regular crap, right? Some rock, whatever. Okay. So to really get this thing going, you have to go a little bit into the core. And the point is, standard model particles, even neutrinos, I've thought about that, even neutrinos don't actually make it all the way in there.
Okay.
The mean free path is short enough. And 10 to the 18 GeV is also above this so-called GZK cutoff. So you can never really get regular protons and things like that up to that energy. Yeah. Yes?
Is it on?
Yeah.
Okay. I was wondering about exploding neutron stars. Could the same thing happen, or can it not penetrate the core?
It's very hard to explode neutron stars because they're dead. Right? They're basically, there's no nuclear fusion going on in a neutron star.
So even like the supernova, even if there was something, because I mean, they could collapse to black holes. I guess they would emit a lot of radiation when they do that.
Yeah, that's due to gravitational collapse, right? That's a different story.
Okay,
Yeah,
okay.
yeah, yeah. So I can't. Yeah, I'm not trying to cause that.
Okay, thanks.
What would cause gravitational collapse?
Look for some kind of dark matter
Yep.
being captured by a neutron star.
Oh, there's a different game people play, which is basically the statement that dark matter gets captured. The capture will eventually cause its own black hole inside the neutron star, and then that black hole will grow up, eat up the star itself. That's possible, but that's different from what I'm talking about, right? There's not actually this super heavy guys kind of thing. Yeah. Okay. So as a rapid review of primordial black hole dark matter parameter space, the current bound is supposed to be somewhere between 10 to the 24 grams. That is the macho bound from the top, and 10 to the 17 grams, because below that, Hawking radiation supposedly would rule it out. The Schwarzschild radii that correspond to this is something like 10 to the minus 4 centimeters to about 10 to the minus 11 centimeters. That's what those masses correspond to. And we're going to think about the fact that this guy is going to go right through this. So it's a tiny black hole, right? It's tiny mass compared to the solar mass. Solar mass is 10 to the 33 grams. Okay? So it's a tiny black hole, tiny gravitational perturbation. It doesn't do much. It just goes right through the star. So the gravitational pull will only be significant very near the event horizon. Okay? That's the only place where it does anything, and it does localized heating. That's what it's going to do. And essentially the claim is that you'll make this thing explode as a supernova if the amount of localized heating is larger than the trigger that I calculated, or rather Frank and Woosley calculated, Timms and Woosley calculated. So this is again the dynamical friction calculation that we saw in the previous part of the talk. So the black hole is going to enter this white dwarf, right? And it's going to enter at an escape velocity. It's about 10 to the minus 2. So this is what's happening. So this black hole is coming in, and here are these carbon guys. And let's say you're at a distance, the carbon, let's say, is at a distance r from the white dwarf, from the black hole. Maybe I should have shown this picture before when I was trying to explain this. So what's happening is that this guy is coming in at a speed which is bigger than the sound speed in the material. You can calculate that. And that means instant approximation holds, which means the carbon is not responding to the other carbons just yet. It's going to move freely for a brief period. What is it going to do? Well, this guy goes through. This carbon gets kicked this way. This carbon gets kicked that way, right? And they're going to go at each other and collide. How much energy are they going to get? Well, the gravitational acceleration is g times the mass of the black hole over r squared. How much time are they going to spend in doing this? The time is the distance divided by the speed that is going through. So this is again the calculation a times t, right? Acceleration times time. That's the velocity the carbon gets. And I want to say the velocity better be greater than MEV, because that's what I want. So that basically sets that the V of carbon should be 10 to the minus 2, because carbon is 10 GeV in mass. And so you can go and do the calculation, how, solve for R, basically, right? I'm going to basically be like, what is the value of R so that I get this right velocity? And you're going to find that the value of R, so essentially all the carbons that is within a region that is 10 to the 4 times the Schwarzschild radius will get kicked to a velocity of 10 to the minus 2. That's what this calculation is, right? I'm basically saying I want to set V carbon to 10 to the minus 2, solve for what is the value of R so that V carbon is 10 to the minus 2. I'm going to find R to be 10 to the 4 R Schwarzschild, which means all the carbon that is within 10 to the 4 times the Schwarzschild radius will get to a temperature of MEV. That's what's happening. And I want this radius to be 10 to the minus 5 centimeters. That's one of the trigger sizes that I calculated, right? Or rather Frank and Woosley calculated. And that basically says that if you have a primordial black hole whose mass is larger than 10 to the 19 grams, as that guy goes through this white dwarf, it will heat up a region larger than 10 to the minus 5 centimeters to a temperature of MeV. Okay, that's the calculation. So basically, we're going to compare this with the trigger size. So we did that calculation, right? So basically, what this basically shows is that if I have black holes of various masses that are going to go through various white dwarfs, when do the white dwarfs blow up? So essentially, the heavier the white dwarf, the more easy it is to blow up because it wants to blow up, which means even lighter mass black holes can destroy it. So a 10 to the 19 gram black hole going through, say, a 1.3 something solar mass white dwarf will blow it up, while if it's a 0.5 solar mass guy, it needs a much bigger black hole to go through, like 10 to the 23 grams or something like that. That's what this plot basically shows. So what are observational constraints on this? A trivial constraint is basically we can go look at known examples of white dwarfs in our neighborhood and be like, that white dwarf cannot exist because of the fact that if it existed and this black hole went through it, it would have destroyed it, right? So there's a limit like that. So this basically says I'm going to assume the ambient density of 0.3 GeV per centimeter cube, and that basically says that if there are known local white dwarfs near us, they would have been destroyed if 10 to the 19 gram black holes had gone through them. So that basically puts a robust limit on those kinds of particles. That's one limit. Okay. The second is to observe supernova rate. These white dwarfs are going to go through, these black holes are going to go through white dwarfs all over the galaxy or even outside the galaxy. So you can go and calculate, if you thought order 1 of the black holes, order 1 of the dark matter was actually in these kinds of primordial black holes, right, 10 to the 21 grams, things of this kind, you can go and calculate what the supernova rate is. Okay, you can kind of see this of the order 1.2 to 0.4 per century per galaxy, something like that. And you want to compare that against the known rate of around 1, all right, or 0.3, I guess, really. So this is kind of where the constraints basically lie. So the fact that we have seen a bunch of white dwarfs that are around 1.28 solar masses puts a pretty nice constraint on white dwarfs between 10 to the 19 grams and 10 to the 20 grams. A supernova rate of around 1 per century knocks off a bunch over there, 10 to the 21 to 10 to the 23, that order. And, there are claimed measurements, okay, I don't know how much I believe them, of white dwarfs in the center of the galaxy that are supposed to be something like 0.5 solar masses. If those measurements continue holding, I don't know how you really know that, okay, you would put limits on even heavier white dwarfs, even heavier dark matter, so mass dark matter, because those would have gone through and destroyed them as well. But that I don't think is that robust. Okay, so this is kind of where that story basically lies. And with that, let me actually conclude, right? So I don't want to read my main conclusions. I'll basically say, when I thought about this stuff back in the day, I had this impression that people understood type 1a supernova. I believed that they were supposed to be things that are supposed to get a Chandrasekhar mass and they blow up. But that is no longer supposed to be true. Okay? Observationally, we have seen enough of these type 1a supernova that there is genuinely a question of what causes them. We have seen some number of supernova that are exploding with super Chandrasekhar masses, that is more than 1.4 solar masses, and people believe that actually comes due to collisions of two white dwarfs hitting each other. We also have evidence for sub-Chandrasekhar mass collisions, okay, less than 1.4 solar masses. That people don't really have a solid idea of exactly what causes them. So could that be dark matter? I don't know. The third class of observations that are very interesting and puzzling are what are called calcium-rich transients. So calcium-rich transients are, white dwarfs that are exploding with something like 0.8 or 0.9 solar masses, right? Way below the actual Chandrasekhar limit. And they're exploding in the middle of nowhere. And by nowhere, I mean in intra-cluster spaces. Okay, there's not a whole lot of stuff going on there. And nobody really has an idea of what actually makes them explode. So I'm kind of more and more curious as to whether or not properties of dark matter, like unusual kinds of dark matter, it's not like the WIMP dark matter, something like this, but cue balls. I talked about primordial black holes simply because it was something easy for me to calculate. Since I wrote that paper, my students did a bunch of other things where you can think about a variety of other dark matter models, typically in a very heavy range, of course, where you can actually cause these kinds of unusual supernovae. So I'm interested both as a question of, as someone who likes to blow things up, what kind of things can you really do, but really just an observational question, right? If you have access to data for like type 1a supernova and stuff like this, is there a correlation between, type 1a supernova rates and dark matter? Are there unusual stellar explosions, for example, like calcium-rich transients happening in the middle of nowhere, which may point us towards some of these more unusual dark matter models. So with that, let me finish my set of lectures. I've been personally motivated not so much by the question of how can I build dark matter models, but really this question of like, look, the parameter space is huge. No matter where I tell you there is dark matter, if someone came and told you, look, the dark matter is here, I know that I can write a model and be very convinced that model is right. It doesn't take that much time to do it. So the real question here is, what is the observational program we must be having to actually probe this large part of parameter space? And to me, it's a very interesting game. So thank you very much.
Thank you very much indeed, Surjeet. Any more questions or comments?
Yes.
Yeah, one up there.
I think this is a follow-up question. When you see a triple 1A supernova, how do you know if like it's a normal Chandrasekhar binary process or it's like dark matter or stuff? Like we discriminate them.
So there are two different questions there. So one is, so let's say you are already convinced that it is a sub-Chandrasekhar mass, because in a sense you look at the luminosity, right? So you know it's not 1.4 solar masses, which a large number of them are. The question is, how can you distinguish, right?
Yeah.
It's a great question. Yeah. So let's think about possibilities, right? So let us say your standard model idea was that it was basically two white dwarfs merging. What that would do is that it would create gravitational waves. It would create gravitational waves at 1 hertz or 0.5 hertz, because white dwarfs are fat. They don't actually make it all the way to LIGO frequencies. So if you had a gravitational wave detector, let's say between a tenth of a hertz and 1 hertz, or a tenth of a hertz and 10 hertz, something like this, you will see gravitational waves from the inspiraling white dwarf, nothing in the optical. Then the thing merges and you explode. So you do this multi-messenger astronomy. You'll be like, I see gravitational waves and now I'm seeing a type 1a supernova. That convinces me that what happened was a merger of this kind. If it's dark matter, what will happen? So there are two kinds of dark matter possibilities. One is basically something like a primordial black hole. It just goes right through and causes the thing to explode. At that point, I don't have a gravitational wave signal to begin with. But when I have this thing plowing through, it will in general plow through off center. So when the thing explodes, it will create gravitational waves. So you will now see type 1a go off and gravitational wave burst at the same time. Okay? So that's how you distinguish a transit. The third possibility, I didn't talk about that here, but it's something, some of the work my students did, and you can build these models where, it's a little bit like these neutron star stories, where the dark matter gets accumulated in the star, and blah, blah, blah happens, and the thing explodes, right? So when that happens, you see no gravitational waves at all, right? Because the entire collapse is happening from the center. So you just see optically that, this thing went off, but it's a super weird event. It's basically a 0.9 solar mass thing exploding, but without a collision of any kind. So I think with multi-messenger astronomy, and should one successfully build a gravitational wave detector between 0.1 hertz to 10 hertz, which I hope they will, that is actually a very realistic way in which we might know in our own lifetimes whether this is what happens. Sure.
Okay, so there are no other questions. Thank you very much, Surjeet, indeed, for your set of lectures. Wonderful.
Recording stopped.